In this session of CCNA series, I will discuss NTP, also known as Network Time Protocol. Network devices such as routers, switches, and firewall have some concept of date and time of day clock. In the previous session of syslog, the log messages included a timestamp with the date and time of the day listed. It is very important for a network admin to make sure that login information and timestamps have the accurate time and date. But how do you make sure the timestamps are consistent and clocks are synchronized? Let's say I have two routers R1 and R2 connected directly, and clock is unfortunately not synchronized between two devices. Then you have a connectivity issue. The link between R1 and R2 goes down. Uh, if you observe the log on the syslog server, when the clocks are not synchronized, the messages from both the nodes will show different times, which makes the messages on two routers look unrelated. With unsynchronized clocks, two routers would have listed practically identical timestamps and made it much easier to troubleshoot or understand the issue. So it makes sense to synchronize those clocks so that all devices have same time of the day. If your clocks are synchronized, then log messages on both the sides will show the same times and it will make easier for troubleshooting. So accurate time stamping is key to root cause analysis, determining when problems occurred and finding correlations. So the NTP provides the means to do just that. So let's go ahead and see what NTP is. NTP, also known as Network Time Protocol, is a protocol designed to synchronize the clocks of devices over a network. NTP allows network devices to request and receive time from a server that in turn receives a precise time from definitive time source like an atomic clock. It enables devices to request and receive UTC from a server that in turn receives precise time from a atomic clock. NTP operates over the UDP and it listens for client NTP packets on port 123. Understanding NTP is important for network administrators managing, securing, planning, and debugging a network, as time is often a critical factor in mapping events together. Let's look at some of the basic NTP configuration. As you know, NTP uses a client-server architecture. One host is configured as the NTP server, and all other hosts are on the network are configured as NTP clients. Servers supply information about the time of the day uh, to clients, and clients react by adjusting their clocks to match. NTP requires little configuration to make it work with single configuration command on each device. You can configure any Cisco IOS device to act in two modes. One is NTP server mode and another one is NTP server or client mode. In NTP server mode, the device acts only as a NTP server and not as an NTP client. The device gets its information from the internal clock on the device itself. And the command to configure it is NTP master with stratum level. We'll discuss about the stratum level later in the session. Then we have NTP client or server mode. The device in this mode, the device acts as a both client and server. First, it acts as an NTP client to synchronize with a server. Once synchronized, the device can then act as an NTP server to supply time to other clients. And the command to configure it is NTP server either address or host name pointing to the server. Next, let's look at NTP reference clock and stratum. NTP is a hierarchical protocol and is divided into stratum, which defines the distance from the reference clock of the time source. So NTP is a hierarchical protocol, okay, and is divided into different stratums. As you can see, stratum 0, stratum 1, stratum 2, stratum 3, which defines the distance from the reference clock of time source. So our reference clock is atomic clock. So a reference clock is a device that sits atop the stratum hierarchy and is typically a cesium atomic or a GPS clock. So a stratum is simply one layer, or you can say hop count, in the network of layers that distribute time across a network of devices. Stratum tell you how many NTP hops away a machine is from the authoritative time source. Here the stratum level 0 to 15 indicates that the device distance to the reference clock. You can see the top stratum level is 0. This is where the most accurate reference clock sources are located. Stratum 0 defines, devices cannot distribute time over a network directly, though hence they must be linked to a stratum 1 time server that will distribute time to stratum 2 servers or clients and so on. So the higher the stratum number, the more timing accuracy and stability degrades. For instance, uh, if you see the switch on the lower side, it has a stratum of 3 and the router has a stratum of 2. Next, let's look at redundancy in NTP. Rather than referencing internal hardware, you can refer a specific time source on the internet or specific NTP server for better accuracy. For instance, I could use NTP to reference NTP servers that use an atomic clock as the reference source as the NTP primary servers. For redundancy, it's better to have two servers. You can design a network so that some of your devices are referencing to those NTP servers and act as both NTP client and server, as in the case of R1 and switch. So the lower level devices can act as a client connected to those nodes. For redundancy, you can have two servers in the setup, as I've shown in the topology. But what if both the servers become unreachable? So the connectivity to reference clocks will be unreachable, and those routers acting as a clients will no longer have trusted sources. Solution is to configure the routers that are connected to NTP servers as server with lower stratum than the NTP server. In case, for example, our NTP server stratum level is 1, so you can configure it at stratum 7. So idea is to make the routers to act as a master when the server is not available. So NTP server used in this example have a stratum level of 1. So the use of NTP master 7 command with much higher stratum will cause routers R1 and R2 to use one of their internal clocks. R1 and R2 to use one of the NTP servers when available and use the internal clock source only when those servers are not connected or the connectivity is lost in this case. So this is how you can have a redundancy in your setup. Another setup which you can have is, for example, for a scenario like for this scenario where you have R4 acting as a NTP server to R2, R3 and R1. On those nodes, you might have configured the client referencing to the interface IP of the server, that is R4, to get NTP messages. But what if the link between R2 and R4 is down? So the NTP connection will be lost between R2 and R4. So in order to avoid such situation, you can also configure loopback interface as the source on the server, so that if it is reachable from other path, and if one of the path goes down, so the redundancy will be there. And you can configure this by using NTP master 4 and NTP source referencing to the loopback. So the loopback is always up. Even if one of the link is down, it can reach via R3. That's it for this session. I hope this was informative for you. Thank you for watching.